looking at this bell work, uh, only so far 2 people have gotten it right, which is telling me, well, it's telling me some stuff. So let's kind of look at this and figure out what's going on. So remember, you have your normal distribution, and then the actual distribution is defined by these models. That's supposed to be underlined right there. So you've got your mean for all of these, and these are different distributions. So you can find the answer to this without doing any calculations. Anyways, let me draw this again. So for the first one, your mean is 140. Just really quickly, if my standard deviations are 20, this is 120, this is 100. So this interval right here, this is the data we're talking about. And this right here is going to be in the ballpark of, I don't know, I'm trying to do some math real quick, 95, 68, so that's going to be 20, 27. That's about 13.5% or so right here. Now, you don't have to know that, but you can say, it's in that ballpark. I'm not sure exactly what it's going to be. You can say, okay, so we have kind of this visual representation of that much of the data is shown. Okay, so if I tried the next one. So now let's say, now my mean is 10, and I'm going from 11 to 12, so it's a standard deviation of 1. So from 11 to 12 being the interval, well, that's the same amount of data, but it's just on the upper end. So, okay, these two are equivalent, so it's probably not going to be one of those two. So now if we look at the third one, the mean is 0. The standard deviation is 1, so this goes from -1 to 1. So here's -2. I guess I'll show 2. So this goes from -1.5 to 0. So this is going 1.5 standard deviations away from the mean. It doesn't even matter what that what that percent is right now. Again, that should put us at about 47.5% right here. But even not knowing that, again, it's a visual thing. So if we look at the next one, I'll just draw another one right here. 1,000 is the mean. I see that from the model that's given. 120 is the standard deviation, meaning that's 1,120 right here. The interval goes from 1,000 to 1,120. It's only 1 standard deviation from the mean. Part C is 1.5 standard deviation. So the correct answer is C. I see 3 of you have now answered that one correctly. So maybe, I don't know where the confusion happened. Maybe just keep in mind the actual numbers represented here, don't determine the percent of the data that we're seeing, because these are our biggest numbers, but really the highest percent is found in C. So hopefully that makes sense. Even if you got it wrong, hopefully you see where you went wrong with it. Okay. Okay, so scatter plots. In the last unit, we were focused entirely on the normal distribution, and those are dealing with one variable. It's a data set, but we're only looking at one variable for each data point. With scatter plots, we're going to be looking at displays where each data point has 2 quantitative variables associated with it. So each point here is a unique case, and the 2 values, so your x and your y value right here. So if I focus on that particular case, we're going to have the x value of what this is it's the national IQ. So it's maybe about 82. And it also has a value associated with it, which is the GDP per capita. So you should know what that is, but GDP, gross domestic product per person. So this shows about 20,000. So about 82 and 20,000. 2 variables associated with one country, and I don't know what country that is. So when we have 2 quantitative variables, scatter plots the display that we choose, and there's, of course, a lot of stuff going along with that. We display our scatter plot with the x-axis always being what we call the explanatory variable, and the y-axis is the response. Those names are self-explanatory, no pun intended, in that the explanatory variable is the one that we presume has some causal effect on the response variable. Now, that cause, it's important to point that out. We'll talk about cause because we have to be very, 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 very careful with that idea. But still, this one is more, the response should be dependent on the explanatory variable. So if we're talking about vehicle weights, if we were thinking one thing causes another, we would probably presume that vehicle weights will affect tread life, but tread life doesn't have any bearing on the vehicle weight. That doesn't cause a vehicle's weight. Again, be careful with cause, but you get the idea of how we treat explanatory and response. So in this diagram, the national IQ is presumed to explain differences in GDP per capita. Now, this is from a book, and it's a controversial hypothesis, and just something to think about. You don't need to answer this out loud, but is it fair to say that IQ would cause the GDP per capita? Could GDP per capita cause national IQ to go up? So, you know, as far as this goes, this one's kind of these tricky situations, like which one is the explanatory, which one's the response, and we'll talk about this more. We're going to come back to this scatter plot throughout class today. Okay, so correlation. And this is the main thing, probably not completely new for you guys, but there are some important things you'll need to be aware of. A correlation is a way of quantifying the strength of the linear relationship between two quantitative variables. And I can't emphasize this enough, it's the linear relationship. We're going to come back to that. Now, specifically, this is what we call Pearson's correlation coefficient, because there are other types of correlation coefficients, but Pearson's is the big one. The actual value of the strength of the relationship is called the correlation coefficient. And again, you don't have to call it, you don't have to include that coefficient, you know, you can just say R is, correlation is, and is understood. So here's the actual formula. It's the same thing written two different formulations here. And the key thing here is that the value can range from -1 to 1. It cannot go beyond those numbers. And either of those extreme values represents a perfect correlation. A value of 0 represents no relation between the two variables. Okay, so pretty straightforward. Any questions on this so far? Okay. Correlation conditions. Now the book has their own special way of referring to these conditions that it's not like an AP way of talking about it. So I'm not necessarily going to use the same names for their conditions, but this is in your textbook on page 152. So you can see these again. So quantitative variables. Of course, the important thing is both variables here must be quantitative. So look at what you're comparing. If one of them's not quantitative, then a scatter plot makes no sense. Straight enough. And we will definitely come back to this idea, but we only find correlations for linear relationships. If it's nonlinear, we can transform it, but that will be something that we handle much later. We'll just talk about it conceptually today. So it needs to, you need to just do a visual check on it and decide if it's linear or not. And then outliers. If there are outliers in the scatter plot, that doesn't mean we can't do a correlation, but you might want to report the value of the correlation with and without the outlier. And what you might want to do, if this is like a real statistical analysis you're doing in the real world, you'd want to investigate that outlier and figure out, why is this an outlier? What's going on here? There might be some really good explanation why it doesn't fit the trend. Okay, so DUFs. This is the new part, kind of new. Just like we used DISCO when we were talking about distribution, so hopefully you remember that acronym. We're going to use DUFs as our acronym for scatter plots. And what we've got is direction for D. Unusual features like outliers would be U. F is form, S is strength. And we will talk about all of these in detail starting now. But again, this is kind of your acronym that'll help you make sure that you do this as like a checklist. Did I talk about direction, unusual features, form, and strength? Check, 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 check. So direction. Really the only thing that we need to say for direction is whether it's a positive or negative one. If you know the actual numerical correlation coefficient, then that is going to be told in the number itself, but you don't have it, no big deal. You can still save some comments about it. So this one in the middle, just anyone can speak up. What direction would you say that that has?
Negative.
Negative. So a few people were saying that. Very good. Yeah. And you just think of like your lines from Algebra 1 and before. That's a negative slope. It's a negative correlation. And kind of the takeaway from this is that as one variable gets bigger, another one gets smaller. So as this x variable gets bigger, your y variable is getting smaller. All right. All right. And this one on the right, we could say this is one that has really no trend at all. So this is one where you probably don't really have any kind of correlation, like a correlation of 0, basically. Unusual features. This we will definitely talk about more, especially in chapter 9. But for right now, you can just note if there are any outliers. And it's worth pointing out, we don't really have a hard and fast rule like, you know, the 1.5 times IQR when we were looking at box plots. But we can still talk about outliers. So in this scatter plot, go ahead, you can annotate, circle where you think a point that might be an outlier. There it is. Yeah, so it's nothing mind-shattering going on, nothing like incredibly complex. You just look at it, say like, that's not part of the trend, so that's an outlier. Okay, very good with that. So we're good with direction, we're good with unusual features. The form that it takes, form refers to whether the scatter plot shows a linear relationship or a nonlinear one. Now, nonlinear relationships could be of all different types. It could be exponential, logarithmic, quadratic, cubic. It could be, you know, square root function. All kinds of different forms that things could take. But for our purposes, all we need to say is it linear or is it nonlinear? And, you know, we'll worry about the other stuff later. So the one on the left, would you call that linear or nonlinear? Anyone can speak up.
Linear.
Linear. Hopefully you guys all agree that's linear. Sometimes it can be a little bit tricky. And maybe we have some debate on this one. Would you call this one on the right linear or nonlinear?
Non-linear.
Okay, so you guys are saying nonlinear. This is one, there's some that are like kind of iffy, and there's analysis we can do that will kind of determine that, but I might agree this looks to be nonlinear, maybe something like that, like an exponential growth going on, or exponential trend, I should say. So anyways, all you need to say, this one appears to be nonlinear, so therefore maybe a correlation coefficient isn't appropriate. Okay, and the last one is strength. So when you look at your scatter plots, you can describe them as, now you can have a numerical amount. You remember that it's between 1 and -1. But generally you'd say something like, oh, it's a very strong or a moderate or a weak correlation or a perfect association, something like that. So if you look at these, you can see some of these are very strong. Some of them are kind of weak. So, and it's kind of a visual thing, and it's no like strict cutoff for what strong, moderate, and weak are. Perfect means perfect, so it'd have to be like a 1 or a -1. But besides that, there's no real cutoff. So if we look at this one right here, would you say that that's a strong, moderate, weak, no correlation? What would you say?
Weak.
Hearing weak. And this is something that we learn through exposure to this quite a bit. This is actually a correlation coefficient of 0.5. And again, there's no like strict cutoff that says, oh, 0.5 means it's moderate. It depends on what we're correlating. But, you know, you could argue this one's a moderate correlation. You could say it's medium weak. You know, you can come up with your own terms. Just make sure it's something that's pretty obvious. So what I'm going to do real quick is get out of this and take you over to this site. Very cleverly, just guessthecorrelation.com. So, and like you can see here, this is actually set up as a game. And this is one where it actually asks you to find guess the correlation coefficient. So here I might guess that's like a 0.1, and it can be surprising. You do this a few times, so it's actually a 0.02. All right, this one, someone guess, what do you think that is?
0.5.
0.5. Okay, be prepared to be surprised with this. Look at that. It's actually pretty much 0.9. Yeah. So, but it's one of these things, after we do a few of these, now this one, what would you guess that one is?
0.1.
0.1?
0.5.
Look at that, that's a 0.54. So these correlations are actually stronger than you might think. So you need to kind of go with your first guess and maybe add a bit to it. These are all positive, so.
0.9.
0.9, let's try that. Oops. There we go. So when you get it right, you get live. You can lose. I'm not going to play this game for too long, but just to show you people. What's that?
I got it right.
All right, good job. So yeah, it's just seeing it a few times and that helps you understand a little better about what is a strong correlation. What does it actually visually look like if you have a strong correlation? This is a very strong correlation. So you might at first think, oh, that's moderate. No, that's actually very strong. Okay, we'll go back to the presentation now. You don't need to go to this website and play it, but if you want to, it's just guessthecorrelation.com. And the one thing is they're all positive correlations. They don't show you any negative ones there. Okay. So let's move here, and we're going to get a little bit of practice. And what I want you guys to do, I'm going to ask someone to speak up. I'm going to show 4 different scatter plots, and I want you to use DUFs to describe it. So describe the direction, the unusual features, the form, and the strength of these scatter plots. Here's the first one. Anyone brave enough to describe that scatter plot?
I'd say it's in the negative direction, and it has like one outlier like right here maybe, and the form, it's linear, and the strength, I'd say it's at like 0.5.
Okay. So I like that description all around. The one thing just with strength is we don't need to specify the number. We just would use an adjective to describe it. So would you say strong, medium?
I'd say medium.
Or moderate, I guess is the word. So yeah, moderate. All right. So you might argue if you'd call that a strong or a moderate. That's kind of one of those in-between cases. But yeah, you said negative. You said there could be an outlier. You can always say it's a potential outlier. And you said linear. There you go. So if you were going to write a sentence, you could say the association between driver's age and max distance to read sign is a negative, moderate, linear relationship with one potential outlier at blah, blah, blah. So there you go. Hopefully that, and very good job with that. Let's try this one. You should be able to do this one pretty quickly.
Direction is positive. I don't see any outliers right now. The form is linear, and then strength is very strong.
Very good. We have a very strong positive linear relationship between carats, size in carats and price. I guess we're talking about diamonds here. And that makes sense. That passes sort of intuition check. Okay, this one. Someone different. Tell me what how you would describe the scatter plot.
I would say no direction, and I don't know if we can tell really if there's any outliers. Non-linear and weak.
Okay, so yeah, we've got, I will say the simple thing with something like this is that when there is basically no association, and this is comparing age to internet usage in hours per week. So according to this data, don't know if it's true or not, but according to this data, it looks like there's no association between age and internet usage. So if there's no association, there's no direction, there's no outliers because there's no trend, and there's no form, there's no strength. So you can just say there's no association. So this is kind of the easy case. All right, and then this one right here.
I'd say it's a positive direction, and there's one outlier at the 40 mark,
Okay, yeah.
and the form is linear, and the strength is, I'd say it's moderate to weak.
Okay. So this is one, it's one of those, again, it's a little iffy. It's a little bit confusing. The direction, yeah, it's positive. Yeah, I see this outlier right here. I agree with you. The form and the strength, the one thing, this is one of these kind of iffy ones, like, is that linear or is it actually got kind of a curve to it?
Now that I look at it again, it looks more exponential now.
Okay. Yeah, and no worries. I wasn't trying to trick anyone necessarily, but because it is one of those tricky things, just in general, where if it's linear or almost non-linear, we do have a way of checking for this, which we'll look into more on, I think Wednesday is when we're going to do that. So there you go. The strength, I'd call this like moderate to even moderately strong. You can add adverbs to it as well. It's like, it's fairly strong, just to hedge your bets a little bit. All right, so hopefully that was clear enough. If you didn't describe it exactly the same way as me, you know, hopefully you weren't too far away. All right, now we're not gonna have as many groups in this class, so some of you, you'll be the only ones talking about it. This is in your textbook, page 164, I believe. And so you'll need to open your textbook to this page, because in a second I'm going to put you into breakout groups. And what I want you to do is, you can see the question here. We've got two variables. Which would you use as the explanatory, which is a response variable if you're making a scatter plot? What would you expect to see in the scatter plot? So you would need to describe it with duffs. Would you expect positive, negative, linear, nonlinear, strong or very weak correlation? So anyways, you've got A, B, C, and D. If you're in group 1 or 5, you're going to look at part A. if you're in group 2 or 6, you're going to look at part B. And then I don't think we're going to have 7 groups here, but anyways, whatever we get up to, if you're in 3 or 7, it's part C, and 4 or 8, you'll be in part D. All right, so any questions on this task?
What page in the textbook is it?
164. Okay, so at this point, I will go ahead and put you into your breakout groups. Okay, so what I want to do is, let me present again. You guys just got back, and someone from group 1 and 5, or 5, if you guys could, someone could volunteer to tell me what your group thought would happen with these 2 variables.
All right, we said for part A that the time in minutes of the long distance call would be the explanatory variable, and then the response variable would be the cost, because a longer phone call will likely lead to a longer cost or higher cost. And then we said it would be positive direction, some outliers depending on the carrier, linear or exponential again depending on the carrier, and then probably a moderately strong strength.
Okay, so something like that. I know those red dots don't show up very strong. All right, does everyone agree? Or does anyone, if anyone disagrees, you can speak up. But if you agree, you can just give some thumbs up in the with the reactions. Okay, looks like I don't see anyone disagreeing with that idea. I think that's fair to say. The one thing I would add to this is that if we're talking about one carrier with a defined rate plan, then not only would it be all these things, but it should be a perfect correlation, because that's defined by a formula, right? So if, oops, I deleted it all. But basically, if we're talking about just one carrier, we should see a perfect line matching up with all the rates based on how maybe there's a flat fee plus cost per minute. I don't think those are necessarily shown up for you guys to see, but there you are. Anyways, let's move on to part B. Someone from group 2 or 6, tell us what you think there.
So we said that the time delay would be the explanatory variable, and the response variable would be the distance from the lightning. And then we said that because time is usually, because normally in this case, you're counting the amount of time it takes for you to hear the lightning. And then after that, you'd calculate the amount of distance it was from your location. And we also said that it's the slope of this graph would be velocity. And in that case, you'd need distance over time. And so distance would have to be the response variable.
Okay. At first I was going to disagree with you, but the way you just explained that, I can buy it. Okay. So I was approaching it from, you are a distance away, that's explanatory. What is the time? But you're saying, here's the time, what is the distance? So I like that. I can work with you. So what is the rest of the graph going to look like?
We said it would be a positive direction and linear.
Positive, linear, and what about strength?
Strength, you said it would be fairly strong, just because the velocity shouldn't fluctuate too much because in theory it should be the same for every
Right.
value.
Okay, I can agree with that. If anyone has anything else they want to add, let me know. But yeah, there can be small things that affect that based on the topography around and the atmospheric conditions at the time. So maybe not perfect, but you know, yeah, pretty darn strong. Okay, next one, part C. Someone from group 3. What did you guys think? Aren't long pauses during class just delightful? I like the reactions there. So let me just get group 3 maybe to think about this. Which is going to explain the apparent brightness or your distance from it? What explains the other? So what goes in the x-axis, I should say?
Would the distance explain the brightness?
I think that's fair to say. That's how I think of it. Of course, you could flip it where if you already know there's a mathematical formulation of it, then you could kind of figure out your distance based on the brightness. And of course, with astronomy, you can figure out your distance from stars based on apparent brightness and stuff like that. But we're thinking of it more just on a local level, a street light. So yeah, distance, and I'll just put B right here for brightness. So knowing this, when you are at a close distance, where's the brightness going to be on its scale? Higher or lower?
It's going to be higher when you're closer to it, right?
Yeah. Closer you are to the light, the brighter it's going to be for you. So, of course, further you are away, the less bright it should be. Now, I guess the only thing to talk about here, the form, do we think it's going to be linear or nonlinear?
Probably linear, right?
This is one of these weird things where technically it is probably nonlinear. There's like these weird sorts of, there's an effect in our brains. We only experience kind of exponential growth in light to see any difference of it, not just a regular change, sort of algebraic growth. It needs to be more of a geometric growth. But anyways, for our purposes, let's just say it's linear enough. And then is it going to be a strong or a weak or moderate correlation?
It'll probably be like a moderate to a moderate strong, right?
I think so. I think so. That's fair to say. So there we go. So this is a brief aside, but when your volume, if you change your volume on your phone from like, if it gives you numbers, like you go from 15 to 16, it's not moving up like, oh, here's 14 to 15, I'm moving up that much. 15 to 16, I'm moving up that much. 16 to 17, it's not moving, it's not changing at a constant rate. It changes by percent. So a change from 14 to 15 might be here. 15 to 16 might be here. 16 to 17 might be like that. And that's the way our brains process changes in volume, in light, and other things like that. That's just a brief aside. It's not related to statistics necessarily. Okay, last one, group 4. What did you think about those two variables? I know you don't want class to end. You want to just keep this going forever.
We said there isn't a correlation between age of owner and weight of car.
I think that's fair to say. And if there's no correlation, it doesn't even make sense to talk about explanatory and response. So that's fair. And just intuitively, yeah, it doesn't seem like there should be any kind of relation. Maybe if someone did this, we'd find surprisingly that there is, but let's pretend like that world doesn't exist, which it probably doesn't. Okay, this is just a brief summary of what you can find on page 156 in your book. You might want to mark that page like with a sticky note or something until you've got this down. And some of you it won't take long. Some of you might want to keep referring back to it. But correlations have properties. So the sign of correlation of the coefficient gives the direction of the association. We've talked about that. Correlation is always between -1 and +1. And correlation treats X and Y symmetrically. This one is maybe not immediately obvious what that means, but if you correlate X and Y, that's going to be the same as when you correlate Y and X. So that is just something important to know. Correlation has no units, and you should always present the correlation just as a decimal, not as a percent. There is something we will show as a percent later, but it's not the correlation. Correlation is not affected by shifting or rescaling the data. It only depends on the z-scores. So keep that in mind if you come across some problems where it's saying, oh, they did this to the data. How does that affect the correlation? It doesn't. I mean, if all they did was rescale, it doesn't. If they add a new outlier data point, it does affect it. Keep that in mind. Correlation measures the strength of the linear association between the two variables. So if it's nonlinear, then our correlation coefficient doesn't work. And correlation is sensitive to outliers, like I was just saying. If you do add a significant outlier, it's going to have a major impact on the correlation. And we will talk about that in future chapters, but these properties, just kind of internalize these, look over it, and make sure that you can recognize it. So where this comes up, there could be a conceptual multiple choice question come up that says, here's this, like which of these correlations, which of these how do I want to phrase this? It could give you a scenario and say that someone, like, why is this incorrect? And you have to think through all the properties and which property is being violated by this scenario. Oh, well, you know, this is nonlinear, so correlation doesn't work. So they're trying to find the correlation of nonlinear associations. So hopefully that's making a little bit of sense of where those properties will come into play, but make sure you do know those. Okay, so this is something you were probably familiar with before this class started. Correlation is not causation. You have probably heard that before. And of course, it's important that we talk about it in this class because this is one of the most common misconceptions. If you have some really strong correlations, people are like, oh, look at this correlation. Obviously, that means this causes this other thing, but that's not true. So again, going back to this example from the beginning of class, national IQ is currently being correlated with GDP per capita. And with real world data, this is about like the best kind of correlation you might find. There's nothing like super strong, generally speaking. So what else could the story of the data be right here? If correlation is not causation, what else could be going on? I won't make you sit here for 30 minutes thinking of something, but if anyone has anything to say. All right, I know it's Monday, so I'm gonna give you guys a little bit of help on this. If you read the chapter, you're familiar with this. lurking variables. Sometimes two variables can be correlated and even very strongly correlated. And that doesn't mean that that's because one causes the other. It's because they're both related to a different third variable, which causes both of them. And that might be the lurking variable. Again, I want to be cautious when we say causes both of them. That would be determined not through a correlation analysis or regression analysis, but it would be determined through other means, maybe through experimentation, which we'll talk about later in the class. So, but bottom line, there could be a reason two things are strongly correlated, not because they have any causal effect on the other, but because there's a third factor. So if you look at this, you've got national IQ and GDP per capita. What lurking variable could come into play for this?
School systems?
There you go. Very good. And that kind of sums it up. That you could take that a lot of different directions, but access to education, quality of education, access to higher education. So maybe that's kind of a lurking variable that explains both of those. So keep that in mind. If you ever see strong correlations, don't immediately assume that there's a connection. Okay. So this, I just want to talk about conceptually. We will not be doing anything like this. And these two examples come straight from the textbook. So if you read, you'll recognize those. When we were given nonlinear relations in a scatter plot, we can, and we will eventually transform them to linear. And this basically means identifying what form the relationship, what the relation is, and then transforming it using an inverse calculation. So in this case, this right here is what we started with. And that takes the form of a square root function, which remember, that's just like a parabola turned on its side. So we could look at that and we could say, I think that's parabolic, or I think that is square root. So how do you get rid of square root? If that's the square root of y, how do we get rid of that? We square it. We do the inverse. So if you square the square root of y, you just get y to the first power, and that's what we're looking for. Linear is the first degree. So anyways, look at what they did here. They took their f-stop of a camera and they squared it. So that took the square root function and turned it into a linear function. And of course, that's going to have a perfect correlation. But, you know, the real world data, you can kind of take that concept as well. So we are not going to be doing that right now. In fact, we won't do that until the end of the semester. But conceptually, I just wanted to point out what's going to be happening. Okay, this, I am actually going to skip over this a little bit because we're going to do this with an example. I will come back to it. These are the steps that you might follow in order to create a scatter plot. And remember, this presentation is a PDF online. So if you need to come back to find out the process, just come back to this page. So you might want to make a note of that. And there's also a way we can find the correlation. Again, I'm going to skip over this a little bit because we're going to do this in the context of a problem. That's the last thing we're going to do today. So I'll come back to these. But here is our problem, and then we will go through and I'll let you guys practice with doing some calculator stuff. Minnesota Department of Transportation hoped that they could measure the weights of big trucks without actually stopping the vehicles by using a newly developed weight in motion scale. To see if the new device was accurate, they conducted a calibration test. They weighed several stopped trucks at a static weight and assumed that this weight was correct. Then they weighed the trucks again while they were moving to see how well the new scale could estimate the actual weight. Their data are given in the table on the next page. So you see your two quantitative variables. We're good there. We're going to make a scatter plot for this data. All right. So what you want to do, and this is, I should mention, number 40 in your textbook. So if you already have that open from the last thing, you can find number 40 to see this data, which is on page 170. So I'm going to go back to this slide. And it's really not that complex in what you do. But you want to input the data into two lists on your calculator. Remember, you hit stat and edit. That takes you to your lists. And you want to just make sure as you're putting this data in, that you put it in order. You don't move anything around because the first data point has to match up with the first data point on the other list. And the only other thing as you're getting this put in, make sure you end up with the same number of data points on each list. If you don't, you're going to get what's called a dimension error, and you won't be able to create a scatter plot. So even if you are still working on the data, I'm just going to describe what to do. It's on the page right there. To find the scatter plot, if you have your two lists complete, you have the same number of data points in each one, and they match up, then you can hit second and stat plot, and that'll take you to all your plots. You want to make sure the plot, whichever one you pick, is on, and the very first type that you can create is a scatter plot. For your X and your Y list, the X should be your explanatory variable. In this case, that's going to be weight in motion. Your response variable will be the static weight. And once you've got that, you can just hit zoom 9. Remember, 9 is zoom stat. So it's going to zoom right to your scatter plot when you do that. Okay. Any questions on that? Hopefully I gave you guys enough time to do that. So another thing you can do while you're looking at the scatter plot, we did this with the box plot, you can hit trace and it'll show you all of your data points. And you can just hit right and it'll go through all of them, all 10. And anyways, that can just show you all that fun stuff. So if you're, I'm not gonna sit here and actually draw it, but except to show kind of, I'd have my driving weight right here and my static weight right here. And you can see what the form of that looks like. I won't draw the points on. So looking at that on your calculator, how would you describe the direction, form, and strength of the plot?
Positive direction. I can only identify like one outlier. Linear form, and then moderately strong correlation.
Okay. So there you go. Now, the couple things I would say, and that wouldn't be like a bad description of it at all, but I would say there's really no outliers on this. That one, I think I know the one you're talking about, the one that's maybe at the top right. Not maybe far enough away to be outside of the trend line. So we might not call that an outlier. And I would probably call this actually a very strong correlation. But besides that, you didn't say anything that was like wrong. Okay, so there you go. Now I'm gonna skip part C. And this is the next thing that you need to know is how to find the actual correlation, the numerical correlation coefficient. So you've got your lists put in. I'm going to go back real quick. And here's what we do for this. It's really not that bad. There's a few things I wanted to point out on this. So first of all, you can get out of the graph and just hit stat, go over to calc. And before you choose anything, notice you have a lot of regression analyses built into the calculator. So you've got your 2 linear regressions, a quadratic regression, cubic, quartic, natural log, exponential, and power regression. Lots of stuff going on. The only one you're ever going to use is number 8, linear regression A plus BX. And we'll talk about this more tomorrow, but just for today, that's the only thing you need to worry about. And then your X and your Y list is exactly the same for this as it was for the scatter plot. So once you've got all that, you just hit enter the whole way through. And it gives you an A value, a B value, an R squared value, and an R. And just this last little bit right here, when you did all that, and hopefully I'm not going too fast, if you didn't see R and R squared, it's because you need to turn diagnostics on. And that's where you're going to see diagnostic on in the catalog. If you need help with that, let me know. But the only thing we're interested in right now is the correlation. We just found it. Okay, so find the correlation. Calculator does that for us. We don't ever do that calculation by hand. And what did you get?
0.9653.
There it is. Of course, we always reserve the letter R for correlation coefficient. So that's constant. Okay, the next one. If the trucks were weighed in kilograms, how would this change the correlation?
It wouldn't change the correlation.
Very good. So if you were sitting there kind of trying to figure that one out, remember the correlation properties. We'll find it real quick. Correlation is not affected by shifting or rescaling the data. It only depends on the z-scores. So yeah, there is no change in the correlation. And if this is like if this is an FRQ, you'd want to write that in full sentence. There's no change in the correlation by converting the weights from pounds to kilograms because blah, blah, blah. It's only affected by z-scores. All right, the last one. Do any points deviate from the overall pattern? Let's just answer that one first. You can just say yes or no.
No.
Yeah, I would say no. I don't see anything that really deviates from the pattern. The last one is the trickier one. What does the plot say about the possible recalibration of the weight and motion scale? This requires a little bit of weight, static, weight, driving. Does anyone have any thoughts about this? Looking at the data, looking at the scatter plot, anyone have any thoughts about possible recalibration of this weight and motion scale?
Maybe you could like change A or B.
Well, we're talking about the actual scale itself. Like, is there a trend in the weight differences that you notice? Okay, so just to not keep you here all the time, remember, if these were perfectly calibrated, we would see a correlation that basically hovers right around a slope of 1. All right. But what we had is something that trends a little bit below that. So we had some data right here. And so what that means is that our calibration is a little bit off. And this is a conceptual thing. You have to think about algebra. You have to think about what does a perfect calibration look like. So 1 slope means that whatever the weight, the driving weight is pretty much spot on with what the static weight is. But we're off a little bit, and it tends to be, if you look at this, I'm going to underline, comparing the weight and motion to the static weight, I'm going to underline the heavier one. So static weight was a little heavier there. Weight and motion was heavier. Weight and motion was heavier. Static, weight and motion, static, weight and motion, weight and motion, weight and motion. I think I got all those right. So generally, the weight and motion tends to be heavier than the static weight. So it's asking a conceptual question here. How would you recalibrate? Maybe we could recalibrate to give a lower weight when we do the weight and motion so that matches with the static weight. And the way that you can see this is like this point right here is further to the right on driving weight than it is up with the static weight. So it's just an interpretation question. Any questions on that? So no heavy calculations with this, but some pretty heavy conceptual stuff to think about. So that's kind of the end of what we're talking about today. The homework is found online. Lots of homework problems right here, but remember, you only need to turn one of them in, and that's specified on the homework. A lot of these, if you're going through and they look redundant and you know exactly what you're doing, it's up to you to get mastery. So just approach it that way. The last thing, and this is something I really want to make sure you guys take care of, sign up for the AP Classroom. All right. And then work on that AP progress check, and then those AP documents. If you've already filled them out for another class, all you need to do is go into my Canvas and say done, submit that assignment saying that you've already done it. If you haven't done it yet, just fill those out and then submit saying that you're finished. All right. If there are questions on this, or if you want to see me go through some homework, you can hang around. Otherwise, you guys can have a wonderful day. So on this right here, there is, okay, more correlation errors. All we're doing with these two is looking at what is wrong with these statements. So for 24A, there is a very strong correlation of 1.22 between life expectancy and GDP. Well, we need to look and we compare that to the properties of correlation, and what's violated right here is this 1.22. There's no way you can have a correlation greater than 1, so this is incorrect for that reason. Part B says the correlation between literacy rate and GDP was 0.83. This shows that countries wanting to increase their standard of living should invest heavily in education. Now remember, this goes back to the idea that correlation is not causation. So we can't say that literacy rate causes GDP. So there might be a third factor that's a lurking variable. So there's just something to keep in mind with that. So the next one is, really it's more of the same. I don't even need to spend much time on this. A survey of the world's nations in 2004 shows a strong positive correlation between percentage of the country using cell phones and life expectancy in years at birth. Does this mean that cell phones are good for your health? So that's saying causation. No, there is a correlation, but it's not causation. And what else might explain the correlation between cell phone, percent using cell phones, and life expectancy? Well, just really quickly, I'd say if you have high life expectancy and you have a lot of people using cell phones, then chances are you live in a country that has a lot of, maybe better healthcare system set up, other advantages. So there's some lurking variables going on. All right, so those are the only ones I was going to formally go over today. Not a whole lot to it. It's a lot of conceptual stuff, but if you find any questions come up, feel free to ask those.